So what I'm going to talk about in this video of physics with Cyrus Ishaq is a very, very important concept of the acceleration of free fall, that is G, right? So this is the acceleration that the objects experience near the Earth's surface, right? And the acceleration of free fall, the acceleration of free fall for a body, free fall for a body or an object near to the Earth's surface, near to the Earth. By near to the Earth, I mean less than 1 kilometer, right? Near to the Earth is a constant. So this acceleration due to gravity, that is G, is constant for objects near to the Earth, that is within the range of 1 kilometer from the Earth's surface. If you go beyond that, this value is going to change. So since we are talking about O-level physics 5054, and so that's why I'm going to explain you why this value is taken as 9.81, but O-level physics will quote it as 10 meter per second square. The actual value of G is 9.81 meter per second square. Since it is acceleration, the units are meter per second square. This is also known as the gravitational field strength, and I'm going to talk about this later in the video on the forces, the weight, and all of that. The unit for that is Newton per kg, and gravitational field strength and gravitational acceleration, both of them are the same thing. So sometimes they ask in the exam that what is the difference between this gravitational field strength and this gravitational acceleration. Both of them are the same thing, right? So the acceleration of free fall near the Earth's surface is given this value 10 meter per second square for O-level physics, right? They have just rounded it off. So for objects close to the Earth, the acceleration of free fall G can be taken to be a constant. Any object, any object falling from rest at a height of less than 1 kilometer is said to be under the influence of a uniform gravitational field. So any object falling from rest, it is falling from rest, right? At a height less than 1 kilometers, 1 kilometers is said to be under the influence of a uniform gravitational field. What I mean by uniform gravitational field here is that this gravitational field is a constant, that is 10 meter per second square. Right? This object, let's say this is the object, right? Let's say this is an object, and it's going to fall downwards, and this object is bound to experience a force of gravity. The force of gravity that this object experiences is known as the weight of the object. So the force of gravity that's going to act downwards on this object is due to this gravitational field strength. Let's say that the mass is m, then the force of gravity, which we also call as the weight of the object, force of gravity that we also call the weight of the object, is the mass multiplied by the gravitational field strength, or mass multiplied by the gravitational acceleration. So mass multiplied by the gravitational acceleration. In other words, we can also write it as weight is equivalent to mg, since force of gravity is equivalent to the weight. This w, this w is the symbol for the weight. So this is the weight, this is the mass, and g is the gravitational acceleration. And in fact, this is derived from the Newton's second law, which I'm going to talk about in the other video on Newton laws. The Newton's second law That is, F is equivalent to mass into acceleration. So if you compare both of these equations, this force is the weight. If I compare both of these equations, this force is the weight, the mass is m, and the gravitational acceleration is in fact the acceleration. And what the acceleration I've already told in the previous video, is the rate of change of velocity. It is the rate of change of velocity, how the velocity changes per unit time, right? So acceleration is the rate of change of velocity. So now let's consider an example in which two objects are falling in a uniform gravitational field without air resistance. When the air resistance comes into effect, the scenario changes. This business is different then. So I'm going to talk about two objects. One of them may be a lighter object and one of them may be a heavier object. And you'll see that if they're thrown from the same distance from the top of the Earth's surface, they're going to fall at the same time. They're going to cover the same distance. They're going to fall at the same time, regardless of their masses. Right? So let's just consider that. So motion of bodies falling in a uniform gravitational field without air resistance. So this thing is very important, this thing without air resistance. When air resistance comes into effect, the things are going to change. And usually in the real life examples, we have air resistance. So I'm going to underline this to emphasize this, without air resistance, right? So in this situation, I'm going to talk about a light object. Let's say I'm going to talk about a feather. I'm going to talk about a feather and a piece of hammer. So one of them is a lighter object and the other one is a heavier object. Let's say this is the feather. This is the feather, and let's say we have a hammer as well. We have a hammer. So this is a hammer and this is a feather. So both of them are thrown at time t is equivalent to 0. Both of them are thrown at time t is equal to 0, and eventually they're going to fall. So now let's consider this hammer has a weight W2, and I'll call this weight as W1. And obviously, the weight of the hammer is greater than the weight of the feather. So W2 is greater than W1. But you'll see that both of them will fall at the same time. So at time t is equal to 0, they are at this point, I'm going to throw them downwards and they're going to fall. So this feather is going to fall and this hammer is going to fall, right? They both are going to fall, and you'll see that how their distance and how their velocity is going to change. You're going to see that. So let's say at this point, this hammer falls a distance. I'll call that distance S1. Let's call this distance S1. This is the displacement when both of them fall. So you're going to see that at time t is equal to 1, the hammer and the feather will fall the same distance. They will fall the same distance at t is equal to 1. At time t is equal to 2, what's going to happen? But before that, I'm going to tell you that the velocity of both of these would be 10 meter per second square. 10 meter per second, I'm sorry. The velocity is 10 meter per second. And at time t is equal to 2, the velocity is increasing. So the velocity v2 is 20 meter per second at time. And you see the distance has also increased. The distance has also increased, and obviously the velocity has increased. So S2 is in fact greater than S1. This is the distance, right? Distance. This S1 is the distance and V1 is the velocity. So you see that S2 is greater than s1. So distance is also increasing and velocity is also increases. It's also increasing. So this is the feather at time t is equal to 2, and the hammer is this. This is the hammer. What happens at time t is equal to 3 is, let's say they fall on the surface of the earth at time t is equal to 3. So now the thing is that the distance is even greater. At time t is equal to 3, the distance is even greater. Now this distance has increased from s2 to s3, and the velocity has also increased 30 meter per second. So this s3 is now greater than s2. And the thing is that both of them fell at the same time and here like this. So you see that this is the trend that you can have. At time t is equal to 0, they started falling. At t is equal to 1, they had a velocity of 10 meter per second, both of them. And then t is equal to 2, they had a velocity of 20 meter per second and then 30 meter per second. The trend that you can see here is that both of them are increasing their velocity at the rate of 10 meter per second every second. From starting from 0, when the velocity was 0, now you see the velocity has increased to 10 meter per second in 1 second. So the acceleration is, since acceleration is the rate of change of velocity, I'm going to say that acceleration at this point is delta v over delta t. So acceleration is from this point to this point, it is 10 meter per second per 1 second. So this is 10 meter per second square. 10 meter per second square, since meter per second divided by second is meter per second square. So as I move downwards, what happens is that the velocity has increased to 10 meter per second, but the time interval, that is delta t, this delta is for the change. So now again the velocity has increased to 10 meter per second in the next 1 second. So delta t here is again 1 second. So the acceleration you see is again 10 meter per second square. The change in velocity is 20 minus 10, that is 10, and delta t is 1. So again you see the acceleration is 10 meter per second square. You see, you can see the values. The values are the same for the acceleration. And again at this interval, from from t2s to t3 seconds, the velocity has increased from 20 to 30. And again the acceleration is, I'm going to write it here now, 30 minus 20 over the time interval is 1, from 2 to 3 seconds. So this is 1. So this is again 10 meter per second square. So you see that acceleration is constant everywhere. So this experiment shows that the acceleration due to the gravity is a constant, and it is given a value of 10 meter per second square. The acceleration due to gravity is equivalent to 10 meter per second square. And you see that they are increasing their speed at a rate of 10 meter per second every second. So they undergo a constant acceleration, and they're going to fall at the same time. And their direction is towards the center of the earth. Their direction is towards the center of the earth. So this direction is always towards the center of the earth. And one important thing here is that your question would be that, well, the hammer is heavier than the feather, so why it is not falling earlier than the feather? So the answer to that question, this is a very common question that students usually ask. So the thing is that you know that the weight here is directly proportional to the mass. So gravitational acceleration is in fact the ratio of weight per mass. Larger the mass, the larger the weight, so they're going to cancel out. They're going to cancel out and they're going to give the same value of g. So in fact, if you're going to write it like this, F is equivalent to ma, and this is F is equal to ma, so A is equal to F over m, right? And let's say the force of gravity on this feather is mg. So I'm going to write here mg. So you see that this m is cancelled out with this m, and A is equivalent to g. And again, you see, for the feather is this. For the hammer, let's say that the hammer has a mass capital M, right? So it's going to fall. The mass is m, and by the Newton's second law, F is equivalent to ma, right? And you know that F over m is equivalent to A, and F is mg, and this is m. And you see that this is going to give the same value, that the masses are cancelled out in the equations, right? So this is A is equivalent to G. So you see that both of them are going to fall at the with the same gravitational acceleration. And this value is known as the acceleration of free fall. This value is the acceleration of free fall. So all objects, whether big or small, all objects all objects, big or small, increase their speed at the same rate. And if I have a speed time or velocity time graph for this, let's say this is the velocity and this is the time. I'm going to call this a speed time graph, since in O levels they have specified a speed time graph. So you're going to see that it is going to be a straight line. Now your question is, why is this a straight line? Because you see, at time t is equal to 1 second, the velocity is 10. At time t is equal to 2 seconds, the velocity is 20. At time is equal to 3 seconds, the velocity is 30. So if I plot these points on a graph, they're going to give me a straight line passing from the origin. And you see that the gradient of the speed time graph, gives the acceleration. If I'm going to find the acceleration, if I'm going to find the acceleration through this speed time graph, what's going to happen? This is the change in speed that the y coordinates are, and this is the change in this in the time interval. So the acceleration is delta v over delta t, and you can see that by yourself. Let's say 30 minus 10, 3 minus 1, and it's going to give you the same value, that is 20 over 2, and that is 10 meter per second square. So the gradient of the speed time graph gives you the acceleration. Since both of the objects are falling in the same direction, the speed and the velocity are the same, right? Okay, let's move ahead. Another thing, if you want to calculate the distance from the speed time graph, you have to take the area under the curve. The area under the speed time graph gives the distance traveled. Right? So both of the objects would have the same speed time graph, as you can see, right? And you can find the distance by that, because if I'm going to give you a very small example. Let's say this is the speed and this is the time. An object, it goes with a constant speed. Let's say the speed is 5 meter per second, and the time is, let's say, 4 seconds at this point, right? So if you calculate the area of this rectangle, the area is going to be length into width, and that is, let's say the length is 4 and the width is 5, so that is going to be 20, right? 20, whatever the units for that, right? For a simple shape, right? But the units that they are going to be 20 meters here, right? They're going to be meters, because the length is in seconds, and the time, the length, this length is in seconds, and the width is in meter per second. So I'm going to write it like this: meter per second multiplied by second. So this is going to give you meters, not meter square. This is going to give you meters. And you know that since distance is speed into time, so the speed here is 5 and the time here is 4, and this is going to give you the same answer as that. So you see that area under the speed time graphs gives you the distance traveled by the object. The area under the speed time graph gives you the distance traveled by the object. So if you want to find the distance traveled by this hammer or the feather, you're going to take this area, right? You're going to take this area, and that's this area. This is going to give you the distance traveled. So distance traveled is going to be half into base into height, since it is a triangle. So half into base is 3 and the height is 30. So it's going to be 90 divided by 2, that is going to be 45 meters. So I hope you enjoyed the video. Stay tuned and subscribe to my channel, Physics by Cyrus Ishaq, and I'm going to come with a lot more videos and a lot more concepts for you guys. Thank you very much. Thank you for watching.